Application of orthogonal complement. First question. Let V be an Euclidean space. V एक Euclidean space है and S be a subspace of V. S be a subspace of V. Now we have to show that. हमें क्या शो करना है? S bar is a subspace of V. Now solution. What is given? We have, हमारे पास है V is a Euclidean space. Euclidean space. And we also have S is a subspace of V. Now by definition, S bar equals to alpha belongs to V such that inner product of alpha gamma equals to 0 for all gamma belongs to S. From definition हमें पता है S bar का definition यही होता है. अभी S is a subspace of V, so S bar contains in V. Now we have to show S bar is a subspace of V. तो S bar को V का सबस्पेस दिखाने के लिए सबसे पहले हमें S bar को नॉन एम्प्टी दिखाना होगा. सो हेयर इनर प्रोडक्ट ऑफ थीटा गामा इक्वल्स टू 0 होगा फॉर ऑल गामा बिलोंग्स टू S. क्योंकि मान लीजिए थीटा इक्वल्स टू R2 टाइप एलिमेंट है तो 0 0 आएगा और गामा इक्वल्स टू लेट एक्स वाई. सो इनर प्रोडक्ट ऑफ थीटा गामा इक्वल्स टू 0 आएगा. ये R2 टाइप के लिए सेटिस्फाई करता है, वैसे ही R3 टाइप के लिए भी इनर प्रोडक्ट ऑफ थीटा गामा इक्वल्स टू 0 ही आएगा. सो दैट इम्प्लाई थीटा बिलोंग्स टू S bar. So we have proved that S bar is a non-empty subset. Now let alpha beta belongs to S bar. Thus inner product of alpha gamma equals to 0 and inner product of beta gamma equals to 0 for all gamma belongs to S. gamma belongs to S के लिए inner product of alpha gamma equals to 0 होगा और inner product of beta gamma equals to 0 होगा by definition. Okay, that is inner product of alpha beta comma gamma equals to inner product of alpha gamma plus inner product of beta gamma equals to 0 plus 0 for all gamma belongs to S. That imply alpha plus beta belongs to S bar. अभी let k belongs to real number. Therefore inner product of k alpha gamma equals to k constant into inner product of alpha gamma, that is equals to k into 0 equals to 0 for all gamma belongs to S. That imply k alpha belongs to S bar. Hence S bar is a subspace of V. Now the second question. Let V be an Euclidean space. V be an Euclidean space and S1 S2 are subspace of V, are subspace of V. Now we have to show that theta par equals to V and V par equals to singleton theta. And the second one is S1 contains in S2, then S2 par contains in S1. Now theta bar equals to alpha belongs to V such that inner product of alpha theta equals to 0, that is equals to V. Also V bar equals to alpha belongs to V such that inner product of alpha beta equals to 0 for all beta belongs to V, and that is equals to theta. Why? Because if alpha equals to theta, not equals to theta, if alpha not equals to theta, then inner product of alpha will be greater than 0. So that is equals to theta. Now for the second one, we have S1 contains in S2. Now let alpha belongs to S2 par. Therefore inner product of alpha beta equals to 0 for all beta belongs to S2. That implies inner product of alpha beta equals to 0 for all beta belongs to S1. Since S1 contains in S2, that implies alpha belongs to S1 par. Thus S2 par contains in S1 par.